So essentially, this new thing we're going to talk about is HBase, and the starting point of the story, from my perspective, is to understand what have you seen as far as MapReduce, Hive, and HDFS is concerned. So the brief contours of stuff which you have seen with MapReduce, Hive, or HDFS is that it is batch only. Is that right?
Yeah.
Right. So since it is batch only, because it is batch only, do you see any issues with that? Issue number one, because it's batch only, is that you cannot handle real-time use cases with MapReduce, Hive, or HDFS. For example, say I give you a use case. I tell you that I am. Say I give you a use case. I say I'm Amazon. Okay. And at Amazon, a guy is actually clicking through a pattern. So he goes and looks for a squash racket. Then he goes, looks for a Nike t-shirt. Okay. Then he goes, looks for a pair of shoes. So what you want to do is, based on this guy's history of shopping, right? As he's shopping around on Amazon.com, he's looking for items related to sport, right? So he's looking for items related to sport, correct?
Yeah.
So you can show him a banner advertisement. You can say on the banner advertisement, hey, buy 2 tickets to the squash championship which is happening near you, etc. So how are you going to detect that he's looking for items in the squash department? Is by essentially taking all his data, his clickstream data, which is happening at this point of time, and then massaging that data, and then finally producing a piece of information out of it, which can try something else, right? Now, you got to remember that this use case is a real-time use case, correct? Do you agree with that? I mean, while his activity is happening, that's when you need to figure this out, correct? Is that right? Guys, is that right? I mean, it's a real-time use case, correct? So because it is a real-time use case, can you guys hear me? Guys, can you hear me?
Yeah, I think I'm fine.
Yeah, okay.
Okay, so it's a real-time use case. It's not a batch use case. If I tell you to architect this use case and I say, use MapReduce, Hive, or HDFS for it. If I tell you to use MapReduce, Hive, HDFS for it, what is the challenge you will see? The challenge you will see is this, right? The challenge you will see here is this, that you will be receiving a lot of data and you will be batch processing it and you will be producing results, say, in half an hour from the activity. So in half an hour, the guy has already left your website. So therefore, this is a use case which has real-time meaning to it. There are real-time impacts or real-time associativity to it, right? So this is why you need in the big data ecosystem an alternative set of technologies to solve such kind of use cases. Number one. Number two, what other problems do you see with MapReduce-HDFS. What other problem do you see with HDFS MapReduce-HDFS? The second problem
update is it's not made for the frequent updates, right?
Yeah, there is on HDFS, the concept of update is not concept of HDFS. The concept on HDFS, the concept of update is practically not there, correct? So the concept of update is not there. So essentially what it does is your updates are basically, addition and then expirations in some way. So you expire certain things. That's how your updates are happening, correct? That's how your updates are happening. So then there becomes a use case. There are these use cases, set of use cases. Let me give you an example. I'll give you an example of the same thing. Say you are a bank, right? And at the bank, every night there is a bunch of activity which happens on the mainframe related to changes in accounts, right? So maybe your account balances are updated, etc., etc. It's not likely that on a given night, all your customers will go and do a bank transaction. So hardly 2% of your customers who are going to do bank transactions every night. So you're running some analysis, you're doing some post-processing of these activities on a big data cluster. The problem becomes is how do you handle change? How do you handle the fact that only 2% of the data coming from mainframe has changed, 98% has not changed, right? So that's where you write MapReduce jobs. You figure out the previous version and the new version. And based on the new version and the previous version, you create new files on HDFS. And after you have created the new files on HDFS, you go ahead and update the records by replacing files, right? As you can see, this concept of update in HDFS and even in Hive is causing you pain. It is causing you pain. And the pain is emanating from the fact that, in HDFS, there is no real concept of update per se. So you as a developer, you are doing that update for yourself. So that's the second thing with HDFS. Any third thing which you see? Any third thing you see? I think, pretty much these are the two things which you see. The third thing which you see is the concept of a record, right? The concept of a record. So what do I mean by concept of a record? What I mean by concept of a record is this, that if I have a file, in that file I have records 1, 2, 3, 4, and I want to do some processing at a record level. So how am I going to do that? How am I going to do the processing at record level kind of a thing? The answer is, you manage change at a file level. You cannot manage change at a record level. Okay. Another thing which you will notice about HDFS MapReduce HDFS is high. Guys, can you mute yourself? Okay. I just muted you. I think it must be Meena. I have muted you. Calling you before. Okay. So the next problem which you see is the record. Okay. So what are the alternative solutions? The alternative solutions, of course, would mean maybe you can start developing a platform which can handle random I/O, which can handle real-time use cases, and can give you some construct about data, right? So you can pretty much lay the data out in some structure which can be then leveraged at at scale. So yeah, Meena, you bring up a very good point. The point you are bringing up is data on a big data cluster immutable? Immutable data meaning that it cannot be changed. That's not an accurate statement, but what you're trying to say is that the cost of changing the data via development cost, via processing cost, there is of course some level of complexity which you have to handle. That's what it is, right? So there is this family of databases and these databases, think of it not like a SQL server or a DB2 or an Oracle, but think of it like more like a different way of persisting data and into a database. And this database, this family of databases are called NoSQL databases. How many of you have heard the term NoSQL database before? How many have you heard the term NoSQL database before?
Yeah, I heard them.
Okay, so can you describe what is NoSQL database?
It's basically a key value pair combination. Like you store records in key and value. That's it.
Okay. So yeah, I mean that is right, but you are just describing a very small. You are describing a very small subset of the databases, right? So the NoSQL databases are really a class of databases which store data and you can access data beyond you can store and access data beyond the regular constructs of SQL. That's really the more precise definition. Okay, so NoSQL is a family of databases where you have essentially 4 categories, right? The 4 categories are document based, key value, columnar, and graphs. Okay. So what is a document, right? The document in NoSQL, what is a document? A document is an XML is a document, a Word is a document, a JSON string is a document. So these are documents. If your data or if your entities can be stored as a document, meaning it's a well-formed document, just like XMLs are, in a database, and the accessibility of that is based on the attributes in the document or a key of that document, maybe the doc ID. Okay, then it is called a document store. Examples of document-oriented databases is MongoDB. So MongoDB is something which stores information as documents. Couchbase is another example for this. Okay. Next comes key value pair. Key value pair is essentially there is a data structure called hash map. Okay. How many of you do not know about hash maps? How many of you do not know about hash maps? How many of you do not know about hash map? I take that everybody knows that. Everybody knows a hash map. So, Meena, can you describe what a hash map is to me? Meena, can you describe what hash map is? Maybe she's on mute. Rahul, do you want to describe what hash map is? What is a hash map, Rahul? Do you know what is a hash map, Rahul? Okay, well, maybe Rahul is also not here. When do you want to describe what a hash map is?
Well, it is again a kind of key value pair. Actually, in the shorthand we say a dictionary kind of thing. I think yeah, it's a dictionary, and I think in the Java world it was called hash table, and the difference was I think it permits the null values and null keys. And
okay, so well, very good. So you described hash map in very different ways. Okay, and I will describe hash map in a very different way. Okay. The way I describe hash map is a data structure. Regardless of language, it is prevalent in almost all programming languages, and it always gives you access in constant time. It's a data structure which gives you access in constant time. There's only one other data structure which gives you access in constant time. That is an array. So if I have an array, if I say A100. I will always get to the 100th element in one shot, in one access. I don't need to go through the beginning or the end of the array, all of that. So array is that data structure.
I think you mean collection, right? You can't get any time from collection. The same thing.
You can get what?
I mean, there is a collection, right? We have like concept of collection. So you meant collection, right? Like list.
Yeah. So list never gives you constant time access. List will never give you constant time access. List will give you a access time, worst case access time, proportional to the size of this list. So if you have 1 million elements in the list, if you're trying to look at supposedly if your element is the 1 millionth element, then you have to go through the beginning all the way to the end to get that element. So worst case access time for that element is O million. So O 1 million. But there are these two data structures. Go ahead. But there are these two data structures, hash map and arrays, which actually gives you access at a constant time, right? So what is an array? Array is basically associated to an index. There is data. Array is essentially associated to an index. There is data. What is hash map? Hash map is associated to a key. There is some data, right? The limitation of an array is this, that every piece of value is subscripted by its location ID, and the location ID is basically 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is an array, right? The problem with that is, okay, I'm fine, and I'm getting constant time, but I really want to make the data a function of its, a function of some attribute. I want to make data accessible at a constant time based on the function of its attribute, right? So that is essentially a hash map, right? The hash map is associated to a key, just like everybody described. Associated to key, there is a value, okay? Associated to a key, there is a value. An array is associated to a location ID. Location ID, there is a value, right? Both of them perform the same thing. They give you the same key functionality, same speed, which is O1. So lock ID gives you the value. The key here gives you the value. So the difference here is this guy. The difference here is this guy. This is the difference between the two, lock ID and key. Key is an attribute of the data which you control. And by virtue of you controlling it, you can associate the value to that key. Okay? So this is hash map. This is an array. But then the next question is, let's peel the onion. So how is it that a hash map is able to deliver you the performance of constant access time? How is that? So there is this wonderful concept in computer science called hashing. Hashing is given a string, given a piece of data. Can I pass it to a function called hash, which maps this data to a unique number? Right? Can I pass this data to a hash algorithm, which passes the data to which causes the data to evaluate to a unique number, say 10? Okay. A simple example of hashing is modulo. Is there a possibility that I can take the number 200 and hash it by number 10, meaning, and I get 0, right? Is there this possibility? The answer is yes, there is a possibility. So that now this data associated to the key 200 will go to the 0th location of the array. So at the end of the day, it is still an array. It is still an array, but data goes to the 0th location. And so on the 0th location, you are going to put 200. Again, if there is another 400 coming, 400 will also go here. 400 will also go here. Okay. If there is 201, it goes to location number 1. Right. So this hashing is the function which can be applied to the incoming data, which hashes it to a unique value, which can then be put into this thing. The hashing is that function which does that for you. So hash map is a data structure which allows you to access anything in a constant time. And the result of this constant time is that no matter what the size of the data structure is, you will always get to the data in almost negligible time. Okay, and the power of this whole thing is coming from the hashing function. Okay, now there is, as a result of having a hash map, where hash map is hashing a piece of data into a series of buckets, right? So there are these many buckets, right? So you have buckets like this: 0, 1, 2, 3, 4, 5, 6, right? And you're hashing your data to these individual buckets. You're hashing the data to the individual buckets. Now, what can happen here is that you can take regions of these buckets. You can say, well, I take these as 3 regions. I can say region number 1, region number 2, and region number 3. I can take these 3 regions and I can store them on multiple medias. I can store them on multiple platforms or storage platforms. Where now I can extend the hashing function. I can extend the hashing function to also give me, based on the incoming value to be hashed, it will also give me the location of where the data point is located. Okay? So what is happening here is, based on the hashing function, I will get a value, incoming value, which will be hashed, and not only the hash will give me the bucket where the data is stored, but also tell me where the bucket is. Based on the hash function, I can come to know where the bucket is as well. Okay? So this power of hashing and hash map, the power of hash map has been exploited in the NoSQL family to the hilt, meaning it is being exploited very much to the hilt. So what they started doing is this, that in the NoSQL family, the first set of databases are called document-oriented databases. So what the document-oriented database does is they say associated to the key, there is a doc. Essentially, that's what document-oriented databases are. What is a doc? Doc is a string, okay? And the string is basically it's an entity, a JSON or whatever, and it is open for you to interpret it as that. That is a document-oriented database. The second family of databases in the NoSQL platform are the key-value databases, right? So essentially what the key-value databases is saying is, associated to the key, there is a value. So associated to the key K1, there is a value V1. Associated to the same key K1, there is a value V2. Associated to the same key, there is a value V3. Okay? So associated to the same key, there is a set of values V1, V2, V3, V4, V5. Example of this type of database is Redis or Riak. Okay? So Redis or Riak, again, it is using the same power of hashing and hash maps on top. Now, there is a problem here. The problem is when you have something as key values and you have a lot of values being there are a lot of values being managed or mapped or stored with a key. Then there is a problem of management. Management means if you have 1 million values associated to a key, then the problem becomes that, hey, listen, how do I handle what value is what entity? Okay? Because see, the way human beings think in key value, the way the human beings think is this, that I have a, associated to a key, for example, social security number. Let the key be social security number. I have his driving history. I have his bank transaction history. I have his personal loan history. I have his travel history. I have his education history. So human beings, they tend to club data of similar type together. Okay, so that they can access or address that clubbing of data together. So they like to call it as subject areas, and they'd like to address it together. So when you have a pure key value database at hand, so all of these is various, like for example in his driving history, you have the fact that he owned 3 cars: Toyota Corolla, Honda Accord, Acura, Nissan Altima. He owned these cars, and at the same time, he went to, say, he went to Stanford. Before that, he went to, Forsyth High. Before that, he went to some elementary school. The problem in this thing is, if you wanted to store this disconnected piece of information in a NoSQL platform like key value pairs, then you need to be in the business of figuring out B1 is related to his education history or driving history. So therefore, there comes this third family of databases, which is essentially a key value based database, but it's called a columnar database. So what columnar databases are is basically the values have been arranged into various subject areas or entities. Okay. So essentially, the associated to key are a set of families. So there is a family F1, there is a family F2, and there is a family F3. Okay. Family F1, F2, and F3. So these families, they store information about a person. Okay. So the concept of a key value pair, a database, key value database, becomes more like a columnar database. Okay. So columnar databases are those associated to a key, K1. There are a series of families, F1, F2, F3. Within these families, there are a bunch of attributes. So in case of this, F1 is his driving history. F2 is his education history. And F3 is his financial history. Okay? Does this make sense?
Yeah.
Yes.
Any
So,
questions?
here in that array, kind of in terms of data set is a array like of what? Hash table, dictionary, like this columnar stuff. What is that? It's like.
No, I couldn't understand. I mean, are you connected by a phone or are you connected again by a PC?
Yeah. Okay, so let me just add it.
Okay. So your question was this. The question is, how is this implemented? Is that the question?
Question was like, now I see this array of key, this whatever you're saying, that's the F1, F2 key value pair, right? Or a particular key, like the driving history record. So this is kind of array, right? In the data structure.
It is not an array.
But an array of something. No.
No.
Okay.
It is a hash map. It's a key value pair of associated to a key. It's not an array. So F1, V1, F2, V2, F3, V3. Is this an array or is it in a hash map? Associated to a key F1, there is value V1. Associated to key F2, there is a value V2. Associated to key F3, there is a value V3. Is it an array or a hash map? It is again a hash map. Okay. So associated to a key, there are a whole bunch of things. Okay. So these are key value pairs. Now again, I mean, I'm trivializing this whole thing, right? I'm trivializing the whole thing by saying what I said, which is columnar databases are a improvement on key value based databases because they allow you to handle a set of columns or set of attributes together. That's an improvement. But there are more improvements, right? The more improvements are that these F1, F2, F3s can now be managed distinctly. They can be managed distinctly to the key K1. Okay. Now, there is a fourth type of database, which is called a graph-based database. A graph-based database is an example. Okay, so an example of columnar database is Cassandra. Cassandra, HBase, these are examples of columnar database. Graph-based database, what you do is you actually store data in form of a graph. What is a graph? A graph has got nodes. What is a graph? A graph has nodes. And these nodes are connected by way of edges. So what is a graph? Graph has got nodes, right? So these are these nodes, right? So there is this Preetpal, there is Saurabh, and there is Ravi. And, right? And then there is this another node called Alpharetta. There is another node called Coming, right? So Preetpal lives in Alpharetta. Preetpal is a good friend of Saurabh. Okay. Saurabh lives in Coming. Okay. Preetpal is also a good friend of Ravi. And Ravi lives in Coming. So now I can query this graph and say, give me all those people who live in Coming and are good friends of Preetpal. Okay. Now you can see what is happening here. What is happening here is, in a traditional world of a RDBMS, these are called relationships, correct? In RDBMSs, these are called relationships, correct? Is that right? No? Yes?
Right.
Yes? No? Yes? Yeah. These are called relationships. And relationships in RDBMSs are manifested as joins. Is that right?
Right.
For joining, if you wanted to, if in case of joins in an RDBMS, what did you have to do? You had to take 4 or 5 entities. In order to join these 4 or 5 entities, you would have these tables lay out next to each other, and you do that. The problem with that is conceptually there is no problem, but implementation-wise there is a problem. The problem with that implementation is that you are accessing multiple objects or data structures to make that happen, right? The join thing which we are talking about, in order to make that happen, you have to join multiple entities on disk, right? Well, there is this way of things called graph, which is an alternative way. There is an alternative way of joining stuff, right? Relationships here are first-class citizens, and the way these relationships are managed are through the concept of a edge. Edge is anything which connects 2 nodes. What are the nodes? Node is Preetpal, Alpharetta, Saurabh, Coming, Ravi. Edges are what? The relationships. Good friend lives in, these are called relationships. So it's a very different way of looking at the data. Now, what is the beauty? The beauty of this is, if you have, say, a 5 or 6 table join, which is going to pull millions of records in a relational database, regardless of what database you use, it will take you a few hours to join these tables. Here it takes milliseconds. The reason is the data is stored as a graph, which is its natural propensity. Relationship is its natural propensity. So data is stored as a graph. Make sense? Does that make sense? Does that make sense?
Yeah.
So example of such a database is Neo4j. Okay. Yeah. Any question?
Which one?
Neo4j. NEO, the number 4 and J. Another example of a graph database is Titan, Titan, Titan. Okay. So these are graphs, and by and large they come in the big data family. Okay. So this is the story number 1 about NoSQL platforms. The second and the third story about NoSQL platform is this, that NoSQL platforms still allow you to store data in an unstructured manner, right? So what is unstructured data? I mean, all this big data thing, you know, people say we are unstructured, non-structured, unstructured data and all that. What do I mean by that? What I mean by that simply is, in the relational world, I model information as a series of tables, and the modeling has a cost. The cost of modeling is I am imposing a structure when the data is to be brought in. So there is a translation when data is coming in into the form in which you are trying to store, and there is a translation when data is brought out. Again, the translation of data coming in versus translation of data going out, you know, there is a cost associated to that. And the cost is the processing cost. The cost is the development cost. The cost is the maintenance cost, etc. So all these NoSQL databases, they say we are not going to impose a structure on the data. Let the data exist as an entity by itself. And therefore, they are better suited to handle various types of data or new values of data which are coming through. Make sense? So that's the second thing about the information. The third thing is the way these NoSQL platforms work, and I gave you the crux, I gave you the reason is, I can split up the data and distribute it on multiple machines. So in that case, it becomes a distributed system. Okay. So the thing about NoSQL platforms, the other two things about NoSQL platforms is that they store data, unstructured data. And the third thing is they allow the power of distribution to be harnessed. How is the power of distribution harnessed? I just gave you an example. HashMap. HashMap is a data structure where the key of the data can be slotted based on a function into a bucket. So the meaning of the data, the key becomes a, you do some intelligent processing on the key to slot it into a bucket. This bucket can be resident not on one machine, can be resident on multiple machines, right? This bucket can be replicated. The bucket can be slotted on machines, it can be replicated, so on and so forth. Okay? So NoSQL platforms, they harness the power of distribution. Okay? So there are these three things. One is real time, second is this, and third is distributability. So this is in general the concept of NoSQL. Okay? So you understand? Do you understand the concept of NoSQL platforms?
Yes.
Okay. So as soon as you introduce, so I'm moving on. So the next concept I will talk to you about is as soon as you introduce the concept of distributability, whenever you have the concept of distribution, which means that I have 3 machines. First, I have these 5 machines. Machine 1, 2, 3, 4, and 5. I have these 5 machines. Okay? I have these 5 machines. And I am distributing a piece of data. Say, for example, I am distributing information about your social security number to these 5 machines. So I've got a social security number SSN1. Associated to that, there is driving history D1, there is finance history F1, there is education history E1, there is medical history M1. So D1 driving F1, E1, M1, right? So I say, okay, let's distribute data for SSN1 like that, and then there is another one called SSN2, there is another one called SSN3. So I will put the D1 over here, D2 over here, D3 over here, and then F1 over here, C1 over here, and E1 over here, and then M2 over here. I will do that. So based on some hashing algorithm or whatever, I distribute the data like this, right? What are the complexities which you have introduced? What is the problem? What are the set of problems you have introduced? Can anybody tell me that by having the data distributed on a set of machines, what kind of problems have you manifested?
So basically, you have to find the related data. You have distributed the data related to a particular entity into different systems. When you are retrieving the data, you may have to see some complexity of finding the related data.
Okay. So the first, the complexity of retrieving the data is very good. But the first problem you introduced is the problem of availability. What does availability mean? What availability means is, say I query for SSN1. I say SSN1, give me the data, right? That involves D1, F1, C1, and M1, right? So what all machines will be hit? The machine number 1 will be hit, machine number F5 will be hit, machine number 4 will be hit. So 1, 5, and 4, these 3 machines will be hit, okay? So what happens if machine number 5 is down? What happens if machine number 5 is down? What kind of problem is happening when machine number 5 is down? That means you cannot service the request. I mean, yeah, you can give him D1, C1, and M1, but F1 is not available, therefore you did not service the request, right? It's not a precise system. So the first problem introduced is of availability, okay, in this system. How can you solve it? Can you solve it?
Yeah, we can replicate the data in different systems.
So,
same data can be replicated.
Yeah, so essentially what you are going to do in that case is you will replicate the data and you will create multiple copies of the data in the cluster, in the set of machines. So F1 is not only resident on 5, but is resident on 3 and 2, right? So what you will end up doing is, you will have F1 resident on right? So you'll have F1 resident on this machine and this machine as well. So you solve the problem of availability, okay? But then as soon as you did this, what is the problem which you introduced? as soon as you did what you did, what is the problem which was introduced? Can anybody tell me?
Updates, data updates.
So the second problem which you introduced was consistency. So the second problem which you introduced is the problem of consistency. What does the problem of consistency mean? The problem of consistency means that, say in your cluster, you have 3 copies of F1 because you wanted to achieve high availability. Meaning, even if F5 is down, your information is still serviceable. The problem with that is, say F1 is a current account balance of this guy at a certain bank. Okay. So what do? You're trying to update every night the value of that current account balance, F1. Okay. So obviously there is some previous amount of say $100 and you want to update it to $150. The problem in that is that you will have to select one of the nodes. You will say either the transaction will be performed on 3, 2, or 5. You will have to say that. Either the transaction will be performed on 3, 2, or 5. Or the transaction can be performed on all of them. Or a transaction is performed to a smaller set of those. Right? Whatever the question becomes 3, 2, or 5. Do I perform the set of transactions on all of them, or a small subset of them, or one of them, right? The point is that at that very same time as the transaction is happening, if somebody accesses the other machine for the same value, if somebody says, give me the value of F1, at the time of the transaction, because it's a distributed system, F1, the value of F1 being presented to this guy over here. This guy over here, the value of F1 being presented to this guy over here, may or may not match the value which is being persisted here. So there is another guy, he is doing a transaction here. So these two values of F1 may not match, correct?
Yeah.
Okay. So how can you solve consistency problems? The way you solve consistency problem is this, that the problem of consistency is solved by introducing the concept of quorum. What is a quorum? Quorum is 2/3 of the machines. Okay. What is a quorum? Quorum is 2/3 of the machine. If 2/3 of the machine know about an activity which is happening at a given point of time, if 2/3 of the machines know about an activity happening at a given point of time, then you can say that any client who would like to come and ask for this information, I can present a consistent view of that transaction to him. Okay? So that brings up the third concept. So basically what it means is that in order to ensure consistency, you have to write out in a synchronous manner, you have to write out a particular value to at least 2/3 of the nodes, 2/3 of the machines. This is called the quorum theorem. Basically, if you don't write it to quorum number of machines, you can't guarantee consistency. But then it brings in a third problem. The third problem is these are networks of machines. The network of machines can actually become subnetworks. So these network of machines can actually become subnetworks, meaning 1, 2, and 3, they are not aware of 5 and 4. And 4 and 5 are not aware of 1, 2, and 3. It is entirely possible. Say there was a network equipment here, and the network equipment looks like this. Okay. So there was network equipment, and the network equipment looked like this, the way I mentioned it. Okay. So the question then becomes is what happens if this line gets snapped? If this line gets snapped, then 1, 2, and 3 do not know about 4 and 5, and 4 and 5 do not know about 1, 2, and 3. Okay. So this is the third problem with a distributed network. Is as you go to achieve consistency, there may be something called partitioning of networks, which can happen, and therefore, there is the third concept of partition tolerance. Okay, it's called partition tolerance. So it says partition tolerance. Okay, partition tolerance. Partition okay. The third problem is the problem of partition tolerance. So what I just described to you is, I was gung-ho about achieving this solution and everything. Is that what I have just described to you is what they call it as the gap theorem. So in a distributed system, what the gap theorem says is you can get 2 of the 3, but not the 3. Either you can say high availability and partition tolerance. In that case, you don't have consistency. Or you can say I want availability and consistency. In that case, you don't have partition tolerance. You can have, so all distributed systems can get 2 of the 3, but not all the 3. So either you can have a database which has this property, or this property. You cannot have databases which can have all the 3. Okay. So these databases, whether it's Neo4j, Cassandra, MongoDB, Redis, Riak, whatever these are, they are an implementation of 2 of the 3, except Cassandra. What Cassandra says is I will give you the choice, meaning the client. I will give the client the choice how he wants to set up his cluster. Does he want the cluster of machines to be set up for C and A, or A and P, or C and P? Okay. C and A, I will wind up today's session at 7:50 Eastern Standard Time. Okay. So C and A and P, or C and P. So that is the thing called tunable consistency, meaning in the gap theorem, you pick your 2. You cannot have all the 3. So how do you achieve consistency? You write to all the nodes. You write to the quorum number of nodes. That sacrifices availability, because availability means that if the information is down on a particular node, I can get it on some other node. But if you want consistency, you have to sacrifice on availability. And if you want consistency and availability, there will be partition tolerance. You can't guard against partitioning of clusters. If the clusters get partitioned, you have to knock out the partitioned part of the cluster. So CA, CP, and AP, these are the 3. The gap theorem is what governs your distributed systems, especially NoSQL platforms. Okay. Can you tell me, based on the gap theorem, what is HDFS? Based on the gap theorem, what is HDFS?
So you mean how it relates to comparison kind of?
Yeah. So based on the gap theorem,
Yeah,
How would you
that's
plot
HBase also works on the same concept where it replicates the data and there is a concept from name node and
yeah,
other
but
nodes, right?
in case of HDFS, what two of the three are you having?
I think CP.
Huh?
CP.
KP.
Yep, it is CP. You don't have availability. Reason you don't have availability is that if the name node goes down, the cluster goes down. I mean,
but I think there is a concept of having multiple name nodes, right? Don't we have the public of name nodes as well?
No, but at a given point of time, it is unavailable, correct?
Okay.
At a given point of time, I don't care if it is a millisecond or 1 hour or 1 day, but for that amount of time, the cluster is unavailable, correct?
Okay.
So that's basically HDFS is the implementation of CP, and it doesn't have a very high availability. It has high availability, but during the time of failure, information is not present or not available to you. So all these databases, even your Oracle is again CP. It's a CP database. If you take an Oracle RAC cluster, it's a CP database. It doesn't have availability. I mean, if the instance is down, it's down. You can't get to your information. So that essentially governs distributed databases. Okay? So the result of today's conversation is I have given you a very high-level overview of what distributed systems are, how distributability is managed, and what all things do you do to achieve distributability and all those things. Okay? So now we go into one of the NoSQL databases called HBase. Okay? So what is the HBase? HBase comes into this family of databases called columnar databases. It comes to the family of databases called columnar databases. HBase came out of a paper. So Google produced a paper called, I think the paper's name was Big Table. So they wrote a paper on how to manage information. And in fact, that actually, out of that paper came out many different databases. Cassandra came out of that paper. DynamoDB came out of that paper. HBase came out of that paper. XML came out of that paper. So a lot of guys came out of that paper. Basically, new approach or a new way to look at information. I mean, new implementation of that paper. So what HBase is a columnar database. HBase is a columnar database. Okay? So in the next few, I mean, when we meet tomorrow morning, right? I will explain to you the model of HBase. So I will explain to you the model of HBase. I will explain to you the read path on HBase. How does read path happen? I will explain to you the write path. I will also explain to you the command line interface for HBase. And hopefully that should be good enough for now. Maybe I'll have to spend 3 hours total to make you go through HBase. I mean, of course, HBase is more than that. But for now, I can tell you about the model read path, write path, and command line. So HBase is called a columnar database. HBase implements CP out of CAP. So it has consistency and partition tolerance. It does not have high availability. Although it does not have high availability, still it's very highly available. For a few milliseconds or even a second, even if the master goes down or something fails on a particular node, the transferring process of that to another node in the cluster is seamless. It's not that hard or difficult to see how it is done. Okay. So HBase is a columnar database. So what are columnar databases? Columnar databases, basically, in your relational databases, there's a concept of a row, right? There is a concept of a row. In columnar databases, there is the concept of a row. What is a row? Row is associated to a primary key, PK1, is column value 1, column value 2, column value 3, column value 4, column value 5 associated to that. And there is a PK. So this whole thing is actually stored as a row in a file. So you have PK1, C1, C2, C3, C4, C5. Then you have a row marker, and then you have PK2, C1, C1, C2, C3, C4. What columnar databases are is basically that you are storing everything as PK1, C1, PK1, C2, PK1, C3, PK1, C4. That's how you are storing the data really. So it's no longer, the concept is no longer of a row. The concept is now of a key value pair. The concept is of a key value pair. So that is the thing about columnar databases. Now, in order for more efficient management, what you are doing is you are saying that this is one family, F1. This is one family, F2. What is family? Family is a very loose construct. Think of family more like, in your relational databases, think of a family more like a table. Okay, so family is a table, right? So if you can imagine and contrast this to your relational databases, what is happening is that associated to a key PK1, there are multiple tables. Okay? So in your relational databases, what will you do? In your relational databases, what are you planning to do? What you will do is you have a table T1, you have a table T2, you have a table T3, and you have a table T4. All of them have the same key, PK1, PK1, and PK1. And you write a query to join these four tables based on PK1, correct? Is that right?
Yeah.
Now in a columnar database, it's a different thing. So the thing here is there is a PK1. Associated to PK1 are four entities. So there is entity T1, entity T2, entity T3, and entity T4. This T1, T2, T3, and T4 are really what we call it as, in relational databases, we call it as tables. So now instead of a join and look up in four different files to get your data, you have 4 entities implicitly being joined by the PK. Now, if you don't have this concept of column families, if you do not have the concept of column families, really T1, T2, T3, T4 have been merged into one family. They are one table, right? So that is why this concept of column family has come about, which is an arrangement of data in a particular format. Okay. So I will take a stop here. And I will open up the floor for any questions you may have. Okay, and then I think we'll wind it up now.